Welcome to Lecture 9 on the irrationality of the square root of 2. So we're going to look at a couple proofs of that, and then look at another thing we can do with a number system involving the square root of 2. I think you'll find the end of this video kind of interesting. So anyway, so just a point of history, the Pythagoreans around 500 BC already understood that the square root of 2 was not a rational number. In other words, it's irrational. And I'm sure there are other ancient civilizations that were aware of that as well, right? So let's look at proof here using the fundamental theorem of arithmetic. All right, so we're gonna proceed by contradiction. Suppose the square root of 2 was the ratio of a over b, and we're assuming that the fraction is in lowest terms, that it's been reduced, right? So you cancel out any common factors. Of course we can do this, right? So there's no loss of generality in supposing that the greatest common divisor of the numerator and the denominator forming the fraction is just 1, right? So usually people say in lowest terms, right? Okay, so if that's the case, then 2 is equal to a squared over b squared, right? And so if we suppose a and b have prime power factorizations using a common set of primes like p1 through, p1 through pk, these are the primes and the prime factorizations of a and b, so we're allowing the powers to either be 0 if it's not present, right, or 1 if it is, or 2 or whatever. By the fundamental theorem of arithmetic, there exist prime power factorizations of a and b. Great. And so then what do we get? We have 2 equals b squared, 2b squared equals a squared, right? That implies that 2 times that squared is equal to that squared, right? And by properties of algebra, this is p1 to the 2f1 da 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 pk to the 2fk, and likewise over here p to the 2e1 and p to the 2ek. Now, so if you look at this, this tells us that 2, right? I'm going to scoot this up here a bit. So this tells us that 2 is equal to pj for something, right? Because if we compare these two prime factorizations, then they have to be matching up, right? I mean, if the prime 2 is here, it has to be over here somewhere, and so that means that there has to exist some j that we can combine. There has to be a j somewhere in this list such that 2 is equal to that piece of j, And so, with that in mind, I have 2f1 plus times times pj to the 2fj plus 1, right? Bringing the 2 into there, and I have it equals to that, right? But that then, by the uniqueness of the prime power factorization from the fundamental theorem of arithmetic, we get that 2fj plus 1 is equal to 2ej. That odd number is equal to that even number. Well, that's impossible, right? Therefore, contradiction, which means that, garbage in, garbage out. So apparently the square root of 2 equals to a over b was nonsensical, and we conclude that, in fact, there is no fraction such that the square root of 2 is equal to a over b. In other words, the square root of 2 is not a rational number. So there you go, proof number 1. And I think that's the proof which is commonly given, all right? Now, the second proof I'm going to give you, let me tell you where I found it. And I think the proof I just told you, you could find any number of places, There's actually something in Jones and Jones which is a little bit different. It's a more general result about the contrapositive. It's usually a contrapositive argument, but I couldn't quite see how to easily convert that to the square root of 2 argument the way it's stated. So I decided to shy away from that one. But this is the Elementary Number Theory by David M. Burton. It's another nice introductory number theory book. And in here somewhere, I don't know if I can find it again. And I didn't really make myself a... I should have put a sticky note in here or something, Oh, here it is. It's on page 42 of this book is where I found this argument. So if you want my source, there it is. It's also a nice book to learn basic number theory from. But try to keep these lectures self-contained, of course. So let me scooch back down here. So here we go. Again, by contradiction, suppose the square root of 2 is a over b. And we're going to, again, assume that a over b are in lowest terms, right, where the GCD of ab is 1. And by Bezout's theorem, there exist integers x and y for which ax plus by is equal to 1. Aha! Well, that's cool, because then we can multiply this equation by the square root of 2, like so, and then what happens? Well, then that gives you square root of 2a x plus square root of 2by, right? Now b, right, is b times square root of 2 is equal to a from that, right? And so that's one thing, right? So we have square root of 2a, assume square root of 2 times b square root of 2, right? But we also have what? Square root of 2 times b is equal to a, right? So make those substitutions here and here, and that gives us root 2 times root 2, right? So 2bx plus ay is equal to the square root of 2, which is, by the way, this is manifestly an integer, right? Integer times integer times integer plus integer times integer is an integer. So the square root of 2 is an integer? Well, that's absurd, right? It's impossible for the square root of 2 to be an integer. Therefore, we find, again, by contradiction, that the square root of 2 is rational. I actually really like this proof. I kind of prefer this proof to the first one, honestly, even though this one doesn't allow me to showcase the fundamental theorem of arithmetic or anything. But I like this proof a lot. Now, I mean, there's a slight gap, right? You'd have to prove that it's impossible for the square root of 2 to be an integer, but that seems like a rather reasonable claim. You could do something like prove the square root function's increasing, and prove that the square root of 1 has to be less than the square root of 4, right? And the square root of 1 is 1, and the square root of 4 is 2, and this would have to be between 1 and 2. There's no integer between 1 and 2, therefore the square root of 2 can't be an integer. That's one line of attack I could think of, but I'm sure there are others to fill in whatever gap you might perceive here. So anyway, then I thought I'd take a stab at a third proof, and let's see how that goes for me. All right. So here's my attempt at a third proof. Proof number 3. All right, here we go. So consider f of x equals x squared minus 2. Well, that is a polynomial with integer coefficients, and it's irreducible by Eisenstein's criteria with p equals to 2. See, because 2 divides the next to leading, it divides 2, but 4 does not divide 2, and that's kind of all you need here. Also, 2 does not divide the leading coefficient, which is 1. So it meets Eisenstein's criterions for irreducibility, and we find this is irreducible. And then I'm like, okay, well, suppose square root of 2 is a over b, all right? Then, of course, we have that that's a 0, and that minus the square root of 2 is also a 0, which by the factor theorem gives me that f of x is x minus a over b times x plus a over b, right? And what I was thinking was I'd be able to get from this to prove that I had a reduction, right, over z. And so my next step was like, well, I'll multiply this by b squared. I got b squared f of x is this, so b squared f of x reduces, right? So b squared f of x is not irreducible over z. But that's not the contradiction I need. I need to show f of x is not reducible, is not irreducible over z for the contradiction here. And so, yeah, it didn't quite work. So as I said, never mind. If you can repair this, though, and complete the argument here, bonus points available. Of course, that's only if you're in my class. If you're just watching this on YouTube, well, you can have free internet points. How about that? Sound good? Let us move along here. So now I'm going to take a few minutes to look at what's known as Q adjoin. This is read Q adjoin the square root of 2. All right. And it turns out that this is a field. All right. So let's talk a little bit what I mean by that. So I should mention algebraic number theory makes use of number theorems, number systems like this to reveal properties of primes as well as the structure of certain Diophantine equations. I will show you such a Diophantine equation in this lecture called Pell's equation. All right. But before we get to that, let's just talk about what these number systems look like and how we can do some things with them. So, first of all, Q adjoin the square root of 2 is the linear combinations, rational linear combinations, a plus b root 2. A and b are rationals, right? If I did z adjoin root 2, it would be a plus b root 2, or a and b are integers. Now, both of these are subsets of the reals, all right? So the rules for addition and multiplication are pretty well already set for us, right? So we know how to add, subtract, multiply, divide, all that good stuff. But I'm going to prove a few theorems about these number systems here. One of the things I'll prove is if you took the ratio of two numbers in z adjoin square root of 2, it is in fact in q adjoin the square root of 2. So fractions of things in z adjoin square root of 2 are actually found in q adjoin square root of 2. Now, in principle, there's no reason to expect that, because it could be that the fractions of these things are in something a little bit bigger than that. But they aren't. Here's why. It's the calculation we talked about in the previous lecture, yeah? Right here. So z over w is a plus b root 2 over c plus d root 2. And then we rationalize that thing. We get this. And then, so notice that c squared minus 2d squared is not equal to 0 for all c and d integers. To see that this is true, you can just try plugging in some numbers, right? Like if you plug in 1, you get 1, right? If you put c equal to 1, we could try putting d equal to 0. That doesn't work. We could try putting d equals to like 1. That doesn't work. If we put c equals to 2, we get 4, right? And then we'd have to put d equal to the square root of 2 to make that work. That doesn't work. And so if you anyway, if you play around with this for a bit, you can easily convince yourself that there are no integer solutions to this, which is good news because that means that this fraction and that fraction are in fact rational numbers which are well defined. And there you have it. So z over w is again of the form rational number plus rational number times square root of 2, which means that z over w is in q adjoin square root of 2 as we wanted. Hooray! So let's finish this video before my power goes out. How about that? It's okay. I got some battery power and I got a cell phone with a light. We'll make it work if we need to. So next theorem, z. Let me cover it up here a bit. Straighten that out. There we go. If z a plus b root 2 is in q adjoin root 2, that means a and b are rational numbers. All right, and this is non-zero. Then 1 over z is again a form of the form q adjoin square root of 2. In other words, you can write it as a rational linear combination of 1 and root 2. Let's see how that works. Here it is. A and b rational, z equals a plus b root 2 not equal to 0. Then, same calculation again pretty much. 1 over z is that I rationalize, right? A minus b root 2 times a minus b root 2. Out pops a squared minus 2b squared in the denominator, and that upstairs. And hey, that's a over a squared minus 2b squared. That's rational. Minus b over a squared minus 2b squared. That's rational. So this is in z adjoin square root of 2. And in fact, by the way, this theorem and the observation that q adjoin the square root of 2 is, a commutative ring with identity. In other words, it's got addition, it's got multiplication. Addition and multiplication commute. They associate and distribute with one another as you want them to. All of that usual fun and games for arithmetic, paired with the fact that every non-zero thing has a reciprocal, right? Has a multiplicative inverse. That makes q adjoin the square root of 2 what's called a field, right? And notice here, by the way, that a squared minus 2b squared being 0 is part and parcel of the square root of 2 being a rational number. So we could be confident that a squared minus 2b squared is, not 0. Because if it was, that would mean, if that was 0 for a and b being rational, that would mean that square root of 2 is a rational number, which we have shown, hopefully convincingly, is not the case. All right, so these are all kind of fun things to look at. Let's turn the page here and look at Pell's equation. All right, what is Pell's equation? Well, Pell's equation is x squared minus ny squared equals to 1. This is known as Pell's equation. Now, this equation is not due to Pell. I'm trying to remember. I want to say Euler was the culprit here. Give me a second here. Let me start. Well, you know what? Another good. While I'm on this show and tell here, check this out. This is A Friendly Introduction to Number Theory by Joseph H. Silverman. This is another nice number theory book. You know, there's like hundreds of nice number theory books, I think, because so many people like to talk about number theory, you know. So let's see here. So he starts talking about this on page 245. What's he have to say about it? He says Pell's equation has a long and fascinating history. Its first recorded appearance is in the cattle problem of Archimedes. This problem involves 8 different kinds of cattle and asks the reader to determine how many there are of each kind. And after a bunch of jibber jabber, it finally gives you Pell's equation: x squared minus, let's see here, that's I think 4,729,494 y squared. And oh wow, that wasn't solved until 1880 by this dude named Amthor, and the solution has 41 digits. Good grief. It was also known in India by Brahmagupta. He describes how to use known solutions of Pell's equations to create new solutions, and in AD 1150, that guy gave an ingenious method with a blah 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 for finding the initial solution. I won't even do that. So, yeah, this is an old problem. He eventually mentions that it's not due to Pell. I think the more recent, in terms of, you know, Europe-centric mathematics, whatever you want to call that, mathematics as it's been popularly passed down in the Western tradition, let's say, it was, I think, let's see here, Bruckner, 1657, Bruckner described a general method for solving Pell's equation, and then J. Wallace described Bruckner's method in another book, and then it was Euler. Yeah, it was Euler. Euler read Wallace's book and he thought it was Pell, but it wasn't. It's actually a lot of different people in a lot of different societies, so let's not argue about it. It's an old and important problem, let's just say that. I wouldn't make a very good historian, right? It's like my ultimate answer to all historical questions at some point or another is like, I don't care. That's not exactly true. I do care a little bit about history. But some of these questions are just too old, and we don't have enough data to really convincingly settle them one way or another, who first found it, you know? Anyway, so here it is. Solution of Pell's equation, x squared minus 2y squared equals to 1, are naturally derived using some algebra and z adjoin the square root of 2 as it happens. So z and w in the square root of 2, z adjoin square root of 2, then zw is also in z adjoin square root of 2. Let's see how that goes. So if you multiply this by that, you get that. And guess what? It's still the same form. Integer plus integer times root 2. Now, this formula doesn't really give you a lot of insight, but the one below it does. Same thing, new symbols. x1, y1 root 2 times x2, y2 root 2 gives me x1, x2 plus 2, y1, y2 plus x1, y2 plus y1, x2 parentheses times square root of 2. All right, so what? Well, this straight away leads us to the following very neat theorem. If x1, y1 and x2, y2 are both solutions to Pell's equation with n equals to 2, then x1, x2 plus 2, y1, y2, comma, x1, y2 plus y1, x2 solves x squared minus 2y squared. In other words, if you set x equal to the first thing and y equal to the second thing, it works in this equation. Let's see why. So we have x1 is a solution, we have y2, x1, y1 is a solution, x2, y2 is a solution. And the thing is, we can factor the equation using, let me zoom in just a bit here since I think I can. So we can factor the equation because it's the difference of squares. And if we got the square root of 2, then 2 is a square, right? So working with the square root of 2, we got that. And we've got that. But then, here's the sneaky part, multiply the equations to obtain this times this times this times that equals to 1, right? And then multiply those out, right? I'll multiply the minus with the minus and the plus with the plus. And what you get is x1, x2 plus 2y1, y2 minus this stuff, and the same thing but with plus this stuff. This is essentially the theorem that I had just before this theorem, right? It's the same calculation again, just multiply it out, right? But then you can unfactor this, right? It's basically of the form a minus b times a plus b, which is a squared minus b squared, right? And so what do we have? We've got x1, x2 plus 2y1, y2, quantity squared minus 2 parentheses x1, y2 plus y1, x2, quantity squared equals 1. In other words, this comma that solves Pell's equation with n equals to 2. That is very, very weird that you can get a new solution from a pair of old solutions just like that. Very, very weird indeed. Certainly, like most equations we deal with don't work like that, you know? You don't find one solution to an equation so you can find another one, at least not in my experience. But it is how Pell's equation works. Actually, the equations here in truth form a group, and so this is one of the earliest examples of a group in mathematics, and then people weren't calling it a group, but it was, right? In the sense that it's like a cyclic group, and if you can find the initial solution, it's like a generator for the group. I'm not going to make that explicit, all right, but just saying. So if I ask students to solve x squared minus 2y squared equals to 1, and then I stare at them awkwardly for about 2 minutes, usually someone will break the silence and my awkward stare by telling me that I should use x equals to 3 and y equals to 2. In a class of 10 people, somebody's going to guess that within 5 minutes, in my experience. And it works. See, because 9 minus 2 times 2 squared is 9 minus 8, which is 1. So that's a solution. Aha! Now we can get more solutions using the method of the proof from the previous page. Let's see how. So if we take 3 plus root 2, which corresponds to the solution 3 comma 2, right? And I multiply that by itself, that should give me, well, that gives me 9 plus 2 times 2 squared plus 12 root 2, which is 17 plus 12 root 2. See, that was the thing, right? Is in this proof we learned that x1 comma y1 being a solution, right, gave rise to x1 plus y root 2, x1 plus y1 root 2 being a corresponding sort of factor of the equation, and if you square that factor, it gives you an equation. It gives you a factor of the squared equation, which is then in turn a solution. Anyway, you can do this, right? This times that gives you that, and then you go, okay, well that means my solution is 17 comma 12. And does it work? Yeah, it does. 17 squared minus 2 times 12 squared is in fact 1, right? And this being as much fun as it is, you can't help yourself but do it again, right? Got to do it again. So if I take 3 plus 2 root 2 and multiply it by my 17 plus 12 root 2, this is the number, the algebraic number which corresponds to the 17 comma 12 solution to Pell's equation, and I multiply this bad boy out, I get myself a 99 plus 70 square root of 2, which gives me the insight, aha, 99 squared minus twice 70 squared is 1. I checked it with my calculator. It is true. And you're like, ah, well, you can't do it again, can you? Oh, yes, we can. So, there you go. The wind outside sounds foreboding. Let's see here. 99 plus 70 root 2, 99 plus 70 root 2. Multiply these out. Gets you 19,601 plus 13,860 root 2. Consequently, I learned that 19,601 squared minus twice 13,860 squared gives me 1. This is very cool. So there are infinitely many integer solutions to Pell's equation, right? There's infinitely many solutions to these. But if you get one of the solutions, like 3 comma 2, you can generate a whole infinite family of that. Now, in principle, you might be like, well, what if somebody guessed, I mean, no one's going to guess this, but what if somebody guessed 17 comma 12 first, and they didn't get 3 comma 2 first, right? Then they might not know about the 3 comma 2 solution, right? So if you start at some level, and then you kind of like generate from there, you could be missing stuff from before. It turns out that the algebra of z adjoining square root of 2 allows us to generate infinitely many solutions from an initial guess, right? But the starting point, though, how do you make that initial guess? That's a much more difficult problem. And if you go back and scour the YouTube comments to my first video on Pell's equations, you'll find having YouTube comment battles with people who are indignant over the fact I haven't showed that a solution exists. There's a reason for that. It's because it's really hard. And so this is elements of completing this show and tell. John Stilwell's Elements of Number Theory. This thing on the cover is Conway's River. Well, that's not quite it, I guess, but if you find his chapter on Pell's equation in here, which is where I think I first learned of it, you know, he looks at these kind of pictures, and if you stare at those long enough and you read this, you know, long discussion about the uniqueness of the river and everything, eventually you get to some sense of how you would find the initial solution. I think that's in there. I'm not 100% sure. I've never quite taught it because it's always like a little bit too much for the class. I'm just saying, if you want to dig further into Pell's equation, there is much more to learn. All right? But anyway, hey, that's it for this time. I just wanted to kind of showcase things we can do with the square root of 2 for this lecture. I hope I've succeeded with that. Anyway, thanks, guys.